1 day ago, this channel filed a report on 3 solar flares that erupted from active region 4,455 inches under 10 hours. We documented the flares, the CMEs, the R-class radio blackouts, the G3 storm watch that NOAA issued, and the trajectory of 3 Earth-directed masses of magnetized solar plasma heading toward this planet's magnetic field. That report covered the departure. Tonight's report covers the arrival, and what arrived is not what left. In the hours since that report was filed, the 2 CMEs associated with the M7, 7 and X1, 0 flares did something that was forecast as possible, but not certain. The faster trailing CME overtook the slower leading one, and the 2 merged. The resulting structure, called a Cannibal CME, carries the combined magnetic energy of both ejections in a configuration more complex and more intense than either would have produced individually. NOAA's Space Weather Prediction Center tracked the merger, updated their forecast, and confirmed that the Cannibal CME was the object arriving at Earth. The G3 Stormwatch issued yesterday has transitioned to active G3 strong conditions, with G4 severe conditions listed as still possible in the current advisory. This is a follow-up report in the most literal sense. The event we covered yesterday generated a child event in transit, a new physical object that did not exist when yesterday's report was filed. A single CME arrival would have been the conclusion of the June 3 story. A Cannibal CME arrival is a development. The physics changed between the reports. The instruments changed their forecast in response. We are changing what we report in response to what the instruments show. The ancient record layer in tonight's report reflects this development as well. Yesterday's package examined traditions that spoke to the solar eruption itself, the departure of solar energy from the Sun. Tonight's traditions address what happens when that energy arrives at Earth, the disruption of the magnetic order, the cascade of effects through the systems that depend on that order, and the eventual restoration of the undisturbed state. 4 traditions, different geographies, different languages, different centuries, the same observable interval, encoded in the vocabulary each culture had available. Before this report closes, all 4 will have been examined with the same care we bring to the NOAA data. The record is continuous, whether we are reading it from a satellite or from a manuscript 4,000 years old. Tell us where you are watching from tonight. The Aurora visibility window for this event is significantly wider than usual. Under confirmed G3 conditions, it extends well into the mid-latitude continental United States and across comparable latitudes in Europe and the Southern Hemisphere. Under the G4 conditions that remain possible, it extends further still. If the sky is clear where you are, and you are north of approximately 45 degrees latitude, step outside when this report ends. The comments section is open. Drop your location, drop what you see, and we will build the real-time map. The briefing begins now. Tonight, the instruments are not predicting. Tonight, they are confirming. What you are about to hear has already been verified through 3 independent sources. The data is live. The event is in progress, and we are filing this report as the readings come in. 1 day ago, we filed a report on this channel covering 3 solar flares that erupted from active region 4,455 inches under 10 hours. That report documented what left the Sun. This report documents what has arrived. These are different events. The departure and the arrival are separated not just by time, but by physics. 2 separate masses of solar material that launched independently have merged mid-transit and are now hitting Earth's magnetic boundary as a single amplified wave. This is called a Cannibal coronal mass ejection. It did not exist when yesterday's report was filed. It formed in the space between the Sun and this planet, 90 million miles from either endpoint, and it arrived tonight. We are going to cover what the live data shows, what the historical record tells us about events at this scale, and then we are going to pull the older layer. 4 separate traditions recorded solar disruption events in language specific enough to examine side by side with what NOAA is reporting tonight. We will reach all of it before this report closes. Before we begin, a word about what we do here. This channel files nightly reports on geophysical and astronomical events, cross-referenced against official agency data and against the oldest human records we can find. We do not sensationalize. We do not fabricate. We take the data, We take the history and we put them side by side and let the pattern speak. If that is the kind of reporting that matters to you, hit subscribe and stay. The data does not stop when we do. Neither do we. Tell us where you are watching from tonight. If the aurora is visible from your location, we want to know. Drop your city or your region in the comments. Previous broadcasts have built a real-time map of how far south the light is reaching. Tonight that map may extend considerably further than usual. The briefing begins now. The first readings arrived at 1:36 UTC on the 3rd of June 2026. NOAA's GOES 1-9 satellite registered an M9. 3. Class solar flare erupting from active region 4455, a magnetically complex sunspot group positioned near the center of the solar disk in the Sun's northern hemisphere. An M9. 3 flare sits at the upper boundary of the moderate category, 1 classification below X class, and it produced an R2 radio blackout, a condition that disrupts high-frequency communication on the daylit side of the planet for minutes to tens of minutes. That was the first event. 7 hours later, at approximately 7 UTC, the same region produced an M7 flare. And then, 4.5 hours after that, at 11:28 UTC, active region 4455 produced an X1 flare, the strongest category of solar eruption on the NOAA classification scale. An R3 radio blackout followed, affecting a broader swath of the daylit hemisphere. 3 significant flares. 3 coronal mass ejections tracked outbound from the Sun. 2 of those ejections confirmed Earth, directed by NOAA's Space Weather Prediction Center, the Met Office Space Weather Team in the United Kingdom, and by independent solar physicists who analyzed the CME trajectories in the hours following the eruptions. That sequence, 3 flares inside a 10-hour window from a single active region, is uncommon enough that NOAA issued a G3 strong geomagnetic storm watch as of the 3rd of June 2026 at 21:17 UTC. The watch covered June 4 and June 5 UTC days. That was yesterday. Here is what the data shows as this report is filed. There is a number in the current NOAA advisory that most coverage of this event has not addressed directly. We will reach it shortly. Active region 4455 carries what NOAA describes as an anti-Hale magnetic configuration. The Hale polarity law, established by solar astronomer George Ellery Hale in the early 20th century, describes the expected polarity orientation of sunspan. The first readings arrived at 1:36 UTC on the 3rd of June 2026. NOAA's GOES 1-9 satellite registered an M9. 3. Class solar flare erupting from active region 4455, a magnetically complex sunspot group positioned near the center of the solar disk in the Sun's northern hemisphere. Center disk positioning is significant. A flare that erupts from the center of the solar disk, as seen from Earth, is positioned to launch material in the most directly Earth-facing trajectory possible. The geometry of the eruption maximizes the probability that the CME will be Earth-directed. The positioning of region 4455 on June 3 was essentially optimal for delivery to this planet's magnetic boundary, an M9. 3 flare sits at the upper boundary of the moderate category, 1 classification below X class, and it produced an R2 radio blackout, a condition that disrupts high-frequency communication on the daylit side of the planet for minutes to tens of minutes. The R scale, which NOAA uses to classify radio blackouts, runs from R1 to R5. An R2 event typically causes limited blackout of radio communication at higher frequencies over the sunlit side of Earth, with some degradation of low-frequency navigation signals. Operators who depend on high-frequency radio for long-distance communication, maritime traffic, aviation on transoceanic routes, emergency services in regions where satellite communication is not the primary backup, experience degraded signal quality, or complete loss during an R2 event. An R3 event, which followed with the X1 flare later that same day, produces wide-area blackout of high-frequency radio communication with a loss of radio contact for about an hour on the sunlit side of Earth, along with degradation of low-frequency navigation signals for 1 to 2 hours. These are documented operational consequences, not theoretical projections. They are graded by NOAA and cross-referenced against actual communication system reports after each major event. The 7-hour gap between the M9-3 at 1:36 UTC and the M7-7 at 7 UTC is itself a data point. When a solar active region produces a major flare, it typically undergoes some magnetic restructuring afterward, a partial release of the accumulated energy that has been building in the field. The fact that region 4455 produced a second significant M-class event only 7 hours after the first, and then an X-class event 4.5 hours after that, indicates that the region's magnetic configuration was not simply discharging accumulated energy, it was actively rebuilding. The continuous flux emergence that NOAA noted, new magnetic energy rising from below the solar surface into the region, was replenishing the energy reservoir faster than the flares were depleting it. This is the behavior of a region that is not winding down. It is the behavior of a region that is being sustained by a source beneath the photosphere. The 3 flares on June 3 may have been not a climax but an interim output from a region still building. The X1 0 classification at 11:28 UTC on June 3 produced the third and strongest event of the sequence. An X-class flare is the highest category on the NOAA scale. X1 0 is the lowest designation within that category, the minimum threshold for an X-class event. The scale within the X category is continuous and open-ended. An X2 0 is roughly twice as energetic as an X1 0. An X10 is 10 times as energetic, and so on. The Carrington Event of 1859, reconstructed from historical records, is estimated to have been in the X40 to X45 range by modern researchers. The May 2024 event that produced the G5 storm peaked at X87, and X10 is a significant event by any absolute standard. It is modest compared to what the Sun is capable of producing. That distinction matters not because it diminishes what is currently happening, but because it establishes the position of tonight's event within a spectrum that extends considerably further in the direction the instruments are pointing. The radio blackout, produced by the X10 R3 conditions affecting the sunlit side of Earth, disrupted communication across a swath of the planet that was in daylight at 11:28 UTC. That geographic swath encompasses Europe, Africa, the Middle East, and parts of Asia and South America. Any radio operator, any aviation dispatcher, any maritime communication system relying on high-frequency radio in that zone at that moment experienced degraded or failed communication for a period measured in tens of minutes to an hour. This is the immediate, practical, ground-level effect of a solar flare before the CME ever reaches Earth. The flare's radiation travels at the speed of light and arrives in approximately 8 minutes. The CME, composed of magnetized plasma, travels much more slowly and arrives in days. The flare is the first wave. The CME is the second. We are now receiving the second wave. There is a number in the current NOAA advisory that most coverage of this event has not addressed directly. We said we would reach it. Here it is. The active NOAA SWPC advisory explicitly lists G4 severe storm levels as still possible in the current event window. G4 is one step above the G3 strong level that has been confirmed as active. On the NOAA G scale, which runs from G1 minor to G5 extreme, G3 and G4 are separated by a threshold that has significant practical meaning for power grid operators and satellite system managers. At G3, the documented effects include irregular voltage corrections possible in power systems at high latitudes, false alarms triggered in protection devices, and satellite drag increases that require occasional orbital correction. At G4, corresponding to KP8 on the planetary index, the documented effects include possible widespread voltage control problems in power systems at high latitudes, some protective systems tripping out key assets from the grid, drag increases requiring more frequent corrections for low-altitude Earth orbit satellites, and surface charging on spacecraft in high-latitude orbits. That is the level above what is currently confirmed. The NOAA advisory has not closed the G4 possibility. That means the storm has not yet settled at its ceiling. The window for escalation remains open. The Cannibal CME designation requires careful explanation because it describes a physical process that occurred in transit after both ejections had already left the Sun. When the M7 flare produced its associated CME, a larger but slower mass of magnetized solar plasma, and then the X10 produced its associated CME, approximately 4.5 hours later, a race began across the inner solar system. The X-flare's CME, though smaller in total mass, was moving at a higher velocity than the earlier ejection. Both were heading toward Earth. The faster object began closing the distance to the slower one. In the space between the Sun and Earth, a gap of approximately 150 million kilometers, which the CMEs were crossing in a matter of days, the trailing mass caught the leading mass. What happens when two CMEs interact is not a simple collision. Solar plasma does not behave like billiard balls. The two masses have their own embedded magnetic fields, the frozen-in magnetic field lines that the plasma carries with it from the Sun. When the two structures interact, their magnetic fields reconnect and merge, producing a single structure with a combined magnetic field topology that is more complex than either parent event. The merged structure carries more total magnetic energy than either CME contained individually and its leading edge. The shock front that arrives at Earth before the bulk of the plasma is typically enhanced in intensity relative to what either individual CME would have produced. This is why NOAA's post-merger forecast explicitly lists G4 as possible, where the original individual CME forecasts might have projected G3 as the ceiling. The merger changed the physics of what is arriving. The DSCOVR satellite at the L1 Lagrange point is the instrument that will provide the most critical real-time data during the arrival sequence. L1 is a gravitational balance point between the Sun and Earth, located approximately 1.5 million kilometers toward the Sun. A spacecraft positioned at L1 is always between the Sun and Earth, drifting slowly in a halo orbit around the theoretical balance point, and provides Earth's forecasters with a preview of whatever solar wind conditions are approaching. When the leading edge of the Cannibal CME reaches DSCOVR, the spacecraft's magnetometer will register the change in solar wind magnetic field orientation in real time. That data is transmitted to NOAA SWPC and updated on the public space weather dashboard. The key measurement is the BZ component of the interplanetary magnetic field, the north-south orientation of the field embedded in the solar wind. When BZ is pointing southward, it is oriented anti-parallel to Earth's magnetic field at the boundary between the solar wind and the magnetosphere. Anti-parallel fields reconnect efficiently. When they reconnect, energy from the solar wind couples into Earth's magnetosphere and drives geomagnetic activity. A sustained southward BZ for multiple hours is what transforms a moderate storm into a severe one. The question that DSCOVR will answer in real time is whether the Cannibal CME carries a sustained southward BZ upon arrival. If it does, the storm will intensify. If the BZ is northward or variable, the storm may remain at the currently confirmed G3 level and not push toward G4. The GOES-19 satellite contributes the complementary data stream, geomagnetic field measurements at geostationary orbit, approximately 35,786 kilometers above Earth's surface. The difference between the readings at DSCOVR and the readings at GOES-19 is a measure of how much the solar wind is compressing Earth's dayside magnetosphere, literally how far the magnetic field boundary is being pushed inward by the pressure of the arriving material. During the May 2024 G5 event, the magnetopause, the boundary between Earth's magnetic field and the solar wind, was pushed inside the orbit of geostationary satellites on the dayside, temporarily exposing those satellites to direct solar wind conditions. NOAA SWPC tracked that compression in real time through the GOES magnetometer readings. The same instruments are running tonight. The infrastructure picture for this storm level is specific and documented. Geomagnetically induced currents, GICs, are the primary physical mechanism by which a geomagnetic storm damages or disrupts ground-based electrical infrastructure. When a geomagnetic storm occurs, the rapidly changing magnetic field at Earth's surface induces electrical currents in any conductor of sufficient length to act as an effective antenna. Power transmission lines, which may span hundreds or thousands of kilometers, are ideal GIC conductors. So are petroleum and natural gas pipelines. So are undersea communication cables, which is less commonly noted but equally real. The specific threat to power grids comes from what GICs do to high-voltage transformers. A transformer operates on alternating current, cycling at 60 Hz in North America and 50 Hz in Europe. A GIC is effectively a very low-frequency current, slow enough to be treated as quasi-direct current by the transformer's core. When a DC bias is imposed on a transformer core, it causes the core to saturate during one half of the AC cycle. A saturated core cannot carry the magnetic flux it is designed for, and the transformer responds by drawing reactive power from the system, generating heat in its windings, and in some cases exhibiting highly nonlinear behavior that produces distorted voltages and currents throughout the connected grid. The heat generated during saturation can accumulate in the transformer's windings and in the structural steel components. The damage threshold depends on the intensity and duration of the GIC, the design of the specific transformer, and whether the transformer has protective systems that can detect and respond to GIC conditions before thermal damage occurs. High-voltage transformers, the large units at the core of bulk power transmission systems, are not mass-produced items. Each one is custom-engineered for the specific application it serves. Manufacturing lead times are measured in months to years, not weeks. The United States grid includes several hundred high-voltage transformers at the highest voltage classes, each one a potential single point of failure if it is damaged by a severe GIC event. The industry has invested substantially in GIC monitoring and protective systems since the 1989 Quebec event. But the protection is not universal, and the geography of risk, concentrated in the regions with resistive basement rock, is not evenly matched by the geography of protection investment. The real-time monitoring infrastructure for GIC risk includes a network of geomagnetic observatories operated by NOAA, the USGS, and their international partners, which measure the rate of change of Earth's magnetic field at specific locations. The rate of change, measured in nanoteslas per minute, is a more operationally useful parameter for grid operators than the absolute KP index because it reflects the intensity of the GIC generating field variation at specific locations. NOAA publishes real-time dB/dt data from the observatory network, and grid operators in high-risk areas use that data to make decisions about whether to pre-position spare equipment, increase monitoring frequency, or implement load adjustments that reduce the grid's vulnerability during a storm peak. All of this monitoring infrastructure is running tonight. The agencies that built it understand the risk. The question is whether this particular storm produces the sequence of conditions sustained southward BZ, peak KP at G3 or G4, duration measured in hours rather than tens of minutes, that would stress the grid in the documented ways. We do not have the answer to that question yet. The storm is in progress. The instruments are running. The historical record, which we are about to examine, tells us what happened the last several times the Sun produced events in this range. There is one additional technical dimension to the Cannibal CME that warrants examination before we move to the historical record, because it distinguishes this event from a simple double CME arrival and has implications for the duration and structure of the storm. When two CMEs merge in transit, the leading edges of both structures interact in a region of compressed plasma called a sheath. The sheath is the turbulent zone that precedes the organized magnetic structure of the CME itself, filled with solar wind material that has been swept up and compressed by the outward traveling plasma cloud. In a Cannibal CME, the sheath of the trailing ejection merges with the body of the leading one, producing a combined structure that has an unusually thick and energetic sheath region at its leading edge. This enhanced sheath is often responsible for the initial geomagnetic activity that begins when the CME arrives at Earth, the period before the organized magnetic structure of the CME itself reaches the magnetopause. The practical consequence is that a Cannibal CME tends to produce geomagnetic activity in two phases. The sheath arrival produces the first geomagnetic perturbation, often with an initial sudden commencement, a rapid increase in the geomagnetic field measured at ground stations worldwide as the leading edge of the compressed solar wind hits Earth's magnetosphere. This sudden commencement is measurable at the surface by magnetometers and by the aurora that accompanies the initial shock. Then, as the organized magnetic structure of the merged CME itself arrives, a second and often more intense phase of geomagnetic activity begins. The Bois orientation of the CME's internal magnetic field during this second phase is what determines whether the storm deepens to G4 or remains at G3. That's something's add. A sustained southward BZ in the CME body drives the most intense ring current enhancement and the longest duration storm conditions. The monitoring infrastructure responds to both phases in sequence. DSCOVR at L1 will detect the sheath's enhanced solar wind parameters before the CME body itself arrives, providing advance warning of the sheath's character. GOES at geostationary orbit will register the magnetopause compression associated with the sheath arrival. The ground magnetometer networks will record the sudden commencement. Then, as the CME body arrives over the following hours, the BZ readings from DSCOVR will update. The KP index will track the storm's intensity in 3-hour windows, and the Aurora will respond to the ring current changes driven by the interaction between the CME's magnetic field and Earth's own field. The full sequence of a Cannibal CME geomagnetic storm may unfold over 12 to 24 hours, with the most intense activity often occurring not at the initial arrival but during the CME body passage. Tonight's event is in that sequence. The initial arrival may not represent the storm's peak. The hours following the initial sheath are the hours to watch. The infrastructure operator community understands this two-phase structure. Power grid emergency dispatch systems are trained to watch the same metrics we are describing here: the real-time KP, the DSCOVR BZ, the rate of change of the magnetic field at ground observatories. When those metrics cross the thresholds that trigger protective action, the response is scripted: pre-positioning of spare transformer equipment, activation of GIC monitoring at transmission substations, reduction of power flows on specific high-risk transmission corridors, and coordination with neighboring grid operators to ensure that if one region needs to take protective action, adjacent regions are prepared to compensate. The protocols are documented. They are being executed tonight, or will be, as the storm peaks. In September of 1859, a telegraph operator in Washington, D.C., named Frederick Royce, disconnected his machine from the power supply to protect it from the surging currents, and then watched it continue to transmit, using only the atmospheric electricity the storm was generating. The wires themselves had become the power source. Another operator in Boston attempted to exchange messages with a colleague in Portland, Maine, with the battery entirely disconnected from the circuit. The messages transmitted clearly for approximately 2 hours. The telegraph network of the eastern United States was, for that interval, running on geomagnetic induction alone. This is the Carrington Event, named for the British astronomer Richard Carrington, who observed the solar flare that produced it on the 1st of September 1859 and made the correct inference, novel at the time and initially contested, that what he had witnessed on the surface of the Sun and what arrived at Earth 17 hours and 40 minutes later were the same event. The transit time of 17 hours and 40 minutes is the fastest confirmed CME arrival ever documented in the observational record. Standard CME transit times range from 1 to 4 days. The Carrington CME moved at an estimated velocity of approximately 2,000 km per second, compared to typical speeds of 500 to 1,000 km per second. To reach that speed, the CME appears to have traveled through a corridor of solar wind that had already been cleared and energized by an earlier eruption, a preconditioned path that allowed the event to accelerate beyond what the Sun normally produces. Some researchers have noted that this preconditioned path mechanism is related to, though not identical to, the Cannibal CME process currently underway. Both involve solar material whose transit is modified by interaction with previously launched solar ejecta. The geomagnetic storm the Carrington Event produced is classified in retrospect at G5 extreme, the maximum level on the NOAA scale, which did not exist in 1859. The DST index, the measure of the equatorial ring current disturbance that serves as the proxy for storm intensity, has been reconstructed from historical magnetometer records by researchers including Jeffrey Love of the USGS and Stuart Nagatsuma. The reconstructed DST for the Carrington Event is estimated at approximately -850 to -1,700 nanoteslas, depending on the reconstruction method. The uncertainty is large, because the magnetometers of 1,859 though carefully maintained at observatories including Kew in London and Cannibal in Bombay, went off scale during the peak of the disturbance. The needle moved faster and further than the instrument was designed to record. The record has gaps where the storm exceeded the instrument's range. We know the event was enormous. We do not know precisely how enormous, because the tools of the era were not calibrated for it. For comparison, the May 2024 G5 event produced a DST of approximately -412 nanoteslas. That event caused measurable satellite orbital decay and GPS accuracy degradation, required protective action by power grid operators in multiple countries, and produced Aurora visible across much of North America, Europe, and parts of the Southern Hemisphere. The reconstructed Carrington DST is between 2 and 4 times more intense, depending on the estimate. The power grid that Carrington would encounter today is orders of magnitude more extensive, more interconnected, and more dependent on the precise functioning of high-voltage transformers than the telegraph network it actually damaged. The calculation of what a Carrington-equivalent event would do to modern infrastructure is one of the more uncomfortable exercises in applied risk assessment, and it has been conducted by researchers at NOAA, at Lloyd's of London, and at the National Academy of Sciences. The conclusions are publicly available. The effects of the Carrington event were global and immediate. Aurora was reported from the tropics. Observers in the Caribbean, in Cuba, in Central America, and in the equatorial Pacific described seeing crimson and green and violet light in the sky at latitudes where aurora is essentially never seen under normal conditions. In the Rocky Mountain gold camps of Colorado, miners woke in the middle of the night believing it was dawn, began preparing breakfast, and discovered only when the aurora pulsed and shifted that the sun had not risen. Telegraph operators across the United States and Europe received electric shocks from their equipment. In some telegraph stations, the paper strips used to record Morse code caught fire from the electrical surges. The disruption was simultaneous across the entire night and dawn side of the planet. There was no geographic refuge from it. The event hit everywhere the storm's energetic particles and magnetic field disturbances could reach, which was everywhere. The observational record that makes the Carrington event scientifically valuable is primarily the magnetometer data from the Kew Observatory in London, which had been collecting continuous magnetic field readings since 1857. The Kew records for September 1 and 2, 1859, are preserved in the UK National Archives. The magnetometer needle moved at a rate and to an extreme that the instrument's paper record could not fully capture. Additional magnetometer data from the Greenwich Observatory, from the Colaba Observatory in Bombay, and from observatories in North America has been compiled and analyzed in the modern research literature. This is documented measurement. It is not folklore. The Carrington event is the best characterized major geomagnetic storm in the pre-electronic era because the observatory network of the mid-19th century had just reached sufficient density and quality to capture it. The second historical parallel is the New York Railroad storm of May 14 to 15, 1921. This event occupies a particular position in the space weather history literature because it occurred in an era when the infrastructure exposed to geomagnetic disruption was considerably more extensive than in 1859, and the consequences were documented in engineering reports rather than in newspaper accounts and personal letters. On the night of May 13 to 14, 1921, a major geomagnetic storm reached Earth. On May 15, the effects became material and documented. The Central New England Railroad experienced simultaneous failures of its signal and switching systems across a wide geographic area, with fires breaking out in the interlocking signal tower at Brewster, New York, caused by the same mechanism as the telegraph fires of 1859. GIC-induced overheating of equipment not designed for that current load. The Swedish city of Karlstad lost telephone service for several hours due to induced currents in the telephone lines. In New York City, the control tower of the New York Central Railroad at 57th Street caught fire, reportedly from induced currents in the signal equipment. Aurora was reported as far south as Puerto Rico, a latitude of approximately 18 degrees north, under conditions that represent one of the lowest latitude auroral sightings in the modern record. The storm is estimated in retrospect at G5 extreme or near to it, placing it in the same order of magnitude as the Carrington Event. What distinguishes the 1921 event in the historical literature is the quality of the engineering documentation that followed. The railroad companies and telephone operators who experienced disruptions filed reports with their management, some of which entered the public record. These reports describe, in operational language, what happens when a power system encounters GIC conditions it cannot absorb. The language is not scientific. It is the language of operations managers describing equipment failures and their sequence. But it provides a ground truth account of the specific ways in which geomagnetic induction translates into real-world infrastructure failure, and that account is consistent with what the theoretical models predict and with what the 1989 Quebec event subsequently confirmed. The distance between 1,921 and 2,026 inches terms of grid infrastructure exposure is vast. In 1921, the total length of high-voltage power transmission lines in service globally was a fraction of what exists today. The interconnectedness of the modern grid, the fact that a failure in one region can cascade through interconnections to affect regions far from the original disturbance, was essentially absent. The modern grid is both more efficient and more vulnerable than anything that existed in 1921. The efficiency comes from interconnection, which allows power to be moved from surplus regions to deficit regions in real time. The vulnerability comes from the same interconnection, which means that a disturbance in one node propagates through the network in ways that isolated systems would absorb locally. The 1989 Quebec event is the modern benchmark. On the 9th of March 1989, a major solar flare erupted. 4 days later, on March 13, the CME it produced reached Earth and drove a geomagnetic storm that is now classified at G5 extreme. The sequence of events at Hydro-Québec began before midnight on March 12, Quebec local time, as the storm's intensity increased. Protective relays on the James Bay transmission lines, long-distance high-voltage lines running from the hydroelectric generating stations in northern Quebec to the load centers in the south, began responding to the abnormal current flows being induced in the lines by the storm. The relays were doing their job, detecting conditions outside normal operating parameters and taking protective action, but they were not coordinated. Individual relays tripped individual lines. The loss of each line increased the burden on the remaining lines, which then triggered additional protective relays. The cascade developed faster than operators could respond manually. At 2:44 local time on March 13, the entire Hydro-Québec grid collapsed. The cascade from first protective relay trip to total blackout took 90 seconds. 6 million people in Quebec lost power. The overnight temperature in Montreal was approximately -10 degrees Celsius. The outage lasted 9 hours and 18 minutes before partial power restoration began. For some customers, particularly those served by distribution systems that required manual restoration procedures, the outage extended through the day. The physical damage included the loss of several large static VAR compensators, reactive power control devices, at the La Grande 4 generating station, and damage to a large step-up transformer at a substation that required replacement. Replacement parts for high-voltage transformer equipment were not available from stock. Lead times were measured in months. The post-event analysis conducted by Hydro-Québec and by the Canadian Electricity Association produced a detailed engineering report that has become a foundational document in space weather risk assessment. The report identified the geology of Quebec as a primary factor in the grid's vulnerability. The Precambrian shield rock underlying the province's territory is among the most resistive in North America, and the high-resistance ground means GIC cannot sink harmlessly into the Earth, concentrating it instead in the transmission infrastructure above. The report also identified the coordination of protective relay responses as a system design vulnerability, and Hydro-Québec subsequently installed dedicated GIC monitoring systems on its transmission network, with automatic detection and protection schemes calibrated specifically for geomagnetic storm conditions. The American power industry examined the Quebec event with intense interest. The North American Electric Reliability Corporation, NERC, subsequently developed standards and guidelines for geomagnetic disturbance planning. Those standards have been strengthened over the years, most recently in response to the May 2024 G5 event, which provided the first real-world stress test of the post-Quebec protection improvements at storm severity levels comparable to 1,989. The results from May 2024 were encouraging in the sense that no major grid failures occurred, and concerning in the sense that the storm drove conditions close to thresholds in several regions and demonstrated that the margin of safety is finite. The 2024 event brought the historical sequence up to date. Active Region 13664, sometimes designated AR 3664, produced a cluster of X-class flares beginning in early May 2024. The largest single flare was an X8-7, the most powerful flare of solar cycle 25, and the most powerful since 2005. The geomagnetic storm that resulted peaked at G5 extreme, with a DST of approximately -412 nanoteslas. Aurora was photographed from Florida, from Texas, from the Caribbean. In Europe, it was visible across the entire continent, including locations in North Africa and the Canary Islands. The storm's intensity was sufficient to cause significant orbital decay for low Earth orbit satellites, requiring SpaceX and other operators to conduct emergency maneuvers to maintain Starlink satellites at their operational altitudes. Several satellites were temporarily lost to tracking and subsequently reacquired. GPS accuracy degraded measurably for aviation and precision navigation applications. The comparison between the 2024 event and tonight's is instructive in both directions. Tonight's storm is less intense than May 2024 inches confirmed terms. G3 with G4 possible is below the G5 that 2024 produced. But tonight's storm is novel in a specific way that the 2024 event was not. It is the product of a Cannibal CME. The merged nature of the arriving plasma means the structure is different from a single CME. The internal magnetic field topology is more complex. The duration of the disturbed solar wind period at Earth may differ from what either individual CME would have produced. The storm in progress right now is not a scaled-down version of 2024. It is a different kind of event with its own profile, and its profile is still being written as this report is filed. The pattern in the modern record is clear. The Sun produces events in this range. When it does, the effects on infrastructure, on communication, on the visible sky are real, documented, and not confined to the worst-case end of the distribution. Storms at G3 and above have caused measurable operational consequences in every decade since the power grid became a significant part of global infrastructure. The trend is toward better protection, but the exposure, the surface area of infrastructure that can be affected, has grown faster than the protection. We are in the storm. The next layer in the record is older than the power grid, older than the telegraph, older than any of the infrastructure the storm is currently stressing. The historical record of major geomagnetic storms extends considerably further back than the Carrington Event, though the quality and specificity of the documentation diminishes as we move earlier in time. What we can recover from pre-instrumental accounts provides a bridge between the modern confirmed record and the ancient traditions we will examine in the following section, a middle layer of human documentation that is neither fully scientific nor purely mythological, but occupies the territory between the two. The most significant pre-Carrington geomagnetic event for which credible documentation exists is the storm of September 1770, which produced Aurora visible across East Asia in a display significant enough to be recorded in official Chinese astronomical chronicles, Japanese court diaries, and Korean observatory records simultaneously. The geomagnetic storm of 1770 has been reconstructed by researchers including Hisashi Hayakawa at Nagoya University, whose work on historical space weather events using East Asian documentary sources has become a significant contribution to the pre-instrumental space weather record. Hayakawa's analysis, published in journals including the Astrophysical Journal, used the geographic distribution and visual descriptions of the 1770 aurora to reconstruct the storm's intensity. The results suggest a DST value comparable to the Carrington event, potentially in the range of -600 to -900 nanoteslas, and a storm duration of several days. The 1770 event appears to have been a major geomagnetic storm of Carrington-class intensity, occurring approximately 90 years before the telegraph provided the infrastructure. to document the infrastructure effects. The 1,770 Chinese records are preserved in official astronomical chronicles, the Tianwenji, or celestial records, that were maintained as part of the official histories of successive Chinese dynasties. The astronomers of the Imperial Board of Astronomy in Beijing were professional observers tasked with recording unusual celestial phenomena, including aurora at unexpected latitudes. Their records from the September 1770 event describe the sky glowing red and green over multiple nights in a display that the Chinese records classify as aurora, the same classification they applied to the far more common polar aurora. The records include information about the geographic extent of the display sufficient for modern researchers to reconstruct the storm's latitudinal extent and thereby estimate its intensity. The Japanese records from the same event are found in court diaries and in the records of provincial governors who were required to report unusual phenomena to the central government. The Tokugawa shogunate maintained a system of provincial administration that produced documentary records across a wide geographic area of Japan, and the 1,770 aurora appears in records from multiple provinces simultaneously. The distribution of these records, from Hokkaido in the north to Kyushu in the south, establishes the extent of the aurora's southward reach in the Japanese archipelago and provides additional data for the intensity reconstruction. The Korean record from the same event comes from the Joseon Wangjo Silok, the Annals of the Joseon Dynasty, a comprehensive official chronicle maintained by royal historians. The Joseon Observatory at Gwanshonde was one of the most active astronomical observation institutions in Asia in the 18th century, and its systematic records include entries for unusual solar and atmospheric phenomena. The 1,770 entry in the Silok describes what the Korean observers saw in language consistent with major auroral display. The convergence of Chinese, Japanese, and Korean records for the 1,770 event from institutions that were maintaining independent observatory records provides a cross-verification that makes the reconstruction of this pre-Carrington major storm scientifically credible. Hayakawa's methodology for using multi-source historical documentation to reconstruct space weather events has been applied to other historical periods as well, producing a reconstruction of major geomagnetic storms extending back several centuries. The database this research is building is slowly filling in the gap between the instrumental record that begins in the mid-19th century and the ancient traditions that extend into the deep past. There are additional documented pre-instrumental aurora observations that indicate major geomagnetic storms in the historical period. The Norse sagas record unusual sky phenomena on multiple occasions that scholars, including Pontus Lindblom, have analyzed as possible accounts of major auroral displays. Medieval European chronicles, particularly those maintained by monastic scriptoria in Ireland, England, and France, contain entries for unusual lights in the night sky at intervals that, when plotted against the reconstructed solar cycle chronology, cluster at expected positions for solar maximum activity. The Venerable Bede, writing in 8th century England, records an unusual red sky that covered the entire visible north on a specific date, a description that matches the appearance of a major low-latitude aurora event. The Chinese Imperial Astronomical Record, the Tianwenji preserved in the official dynastic histories, contains the longest continuous series of astronomical observations in the world, spanning more than 2,000 years. These records have been analyzed by scholars including Xu Zhentao and the Japanese researcher Keiichi Hayashida, who identified aurora records in the Chinese texts and used their distribution across time to reconstruct the approximate chronology of the solar cycle, extending back to approximately 200 BCE. The analysis reveals a cyclical structure in major solar activity that is consistent with the modern observed 11-year solar cycle, demonstrating that the solar activity we are measuring tonight is not a new phenomenon. The Sun has been running this cycle throughout the recorded human period. The events at the peak of each cycle produce, with regularity, geomagnetic storms at G3 and above. The record documents this across 22 centuries. Tonight's event is one data point in a very long series. The 1989 Quebec event produced something that most historical accounts do not emphasize: a concurrent major geomagnetic storm effect in Japan that caused satellite telemetry. disruptions, and a concurrent failure of spacecraft systems that had been designed without adequate radiation hardening for G5 event conditions. NOAA's GOES weather satellite experienced sensor anomalies. The Navy's communication satellite, TDRS-1, experienced a massive signal disruption. Multiple other spacecraft entered protective safe modes. This aspect of the 1989 event established the space assets vulnerability dimension of major geomagnetic storms in a way that hadn't been documented in the telegraph and power grid. Failures of 1859 and 1921, because in 1989 there were satellites to affect. The current satellite environment is orders of magnitude more extensive than 1989. As of 2026, there are approximately 10,000 active satellites in Earth orbit, the vast majority of them in low Earth orbit. The Starlink constellation alone accounts for several thousand of them. The radiation hardening standards and autonomous safe mode protocols have improved substantially since 1989. But the sheer number of assets in orbit means that even a fraction of a percent disruption rate affects hundreds of satellites simultaneously. The GPS degradation that a G3 to G4 event produces is not a failure of individual satellites. It is a systematic degradation of the ionospheric conditions that the GPS signal must travel through to reach receivers on the ground. The ionosphere, energized by the geomagnetic storm's particle injection, becomes an irregular refracting medium that introduces errors in the GPS ranging calculation. Those errors are measurable, they are well characterized from previous events, and they affect every GPS receiver in the affected area simultaneously. The full scope of what a G3 to G4 event touches: power grids, satellite systems, GPS accuracy, high-frequency radio communication, polar aviation routing, pipeline corrosion monitoring systems, railway signal systems, represents the accumulated exposure of a modern civilization whose infrastructure was built, largely, without geomagnetic storm resistance as a primary design criterion. The improvement since 1989 has been real but incomplete. Tonight's storm is running against that infrastructure, and the instruments will tell us how far it ran before the night is over. The bridge between the historical and the ancient deserves its own moment, because it is not self-evident. Moving from Quebec in 1989 to the Norse Eddles requires an acknowledgement that the two records are different in kind, and that the connection between them is not one of direct inheritance but of parallel observation. The people who compiled the Grimnismal were not reading about the March 1989 Hydro-Québec blackout. The engineers who analyzed the Quebec grid failure were not consulting the poetic Edda. The connection is the sky itself, the observable phenomena that a geomagnetic storm produces at the surface of the Earth and in the visible atmosphere. Both groups of observers saw versions of the same phenomena. They encoded those observations in the most durable formats available to their respective cultures. The format changed. The phenomenon did not. What the historical parallels establish is a chain of documentation. From tonight's NOAA advisory, backward through 2024, through 1989, through 1921, through 1859, backward still to the 1770 East Asian Aurora records, and then into the pre-instrumental documentary record maintained by medieval monasteries, Chinese imperial observatories, and Norse skulls. The chain is not unbroken. There are gaps where the documentation is sparse, where the events that occurred left no surviving written trace. But the chain is long enough, and its individual links are specific enough to establish that this category of solar event, the arrival of major geomagnetic storm conditions at Earth, recurs with regularity across the full span of human skywatching. Tonight is one instance in a series that extends further back than any of our monitoring systems and will extend further forward than any of our current infrastructure. That is what the ancient record adds to the modern data. Not proof of anything supernatural, not confirmation of any specific cosmological claim. Something more modest and more durable, evidence that the sun has been doing this for as long as humans have been watching, and that the humans who watched carefully enough to preserve their observations left records that are worth reading alongside the NOAA advisory. The pattern in the modern record is clear, but we do not stop at the modern record. There is an older layer, tablets, manuscripts, oral traditions, documented predictions, that logged events matching this signature long before our instruments existed to confirm them. That layer is what comes next. The Norse cosmological tradition, preserved in the poetic Edda, specifically in the poems Grimnismal, Vafthrûdnismal, and Völuspá, contained in the 13th century manuscript known as the Codex Regius, though reflecting oral tradition of considerably older provenance, describes the behavior of the Sun in terms that modern solar physicists have noted with interest. The Norse understood the Sun not as a static object, but as an entity in motion, pursued, contested, and capable of generating disruption that reached the surface of the world. This is not metaphor divorced from observation. The Norse were a seafaring, sky-watching people whose navigation depended on solar and stellar positioning with sufficient precision to cross open ocean without instruments. Their cosmological descriptions of the Sun's behavior were not purely theological. They were the product of a culture that needed to understand the sky to survive. In Grimnismal, the poem that describes the structure of the cosmos as revealed by Odin himself during a period of ordeal, the Sun's passage across the sky is described as requiring a shield positioned between the fire of the Sun and the surface of the Earth. The shield is named Svalin, meaning the cooler or the chiller, and the poem states explicitly that if Svalin were to slip from its position, the mountains and the sea would burn. What the ancient Norse were encoding in mythological language is the existence of a filtering and moderating mechanism between solar radiation and the planetary surface. The loss of that mechanism produces scorching of the physical world. The imagery is not decorative, it is functional. The Sun's fire is real and potentially destructive. Something stands between it and Earth. When that something fails or is displaced, the consequences are material. Modern readers may dismiss the Svalin passage as pure mythology. What makes it worth examining tonight is the specificity of the claim. The shield does not protect against all solar energy. The Sun continues to function normally while the shield is in place. The shield moderates excess energy. What it blocks is the overage. The concept of a moderating filter that can be disrupted, producing a delivery of solar energy to the planetary surface in excess of the moderated norm, is precisely what Earth's magnetosphere does and fails to do during a major geomagnetic storm. Under normal conditions, the magnetosphere deflects and moderates the solar wind, channeling it around and through the polar regions in a controlled dissipation. Under storm conditions, when a Cannibal CME compresses the magnetosphere, when the interplanetary magnetic field couples efficiently with Earth's field, when the ring current strengthens and the polar electrojet intensifies, the moderation fails, and the energy delivery to Earth's surface exceeds the normal envelope. Svalin slips. The mountains feel it. The scholarly tradition that has examined this passage includes the work of Rudolf Simek, whose Dictionary of Northern Mythology, Boydell and Brewer, 1993, is the standard reference for Old Norse cosmological content, and the broader field of comparative mythology as assembled by scholars including Georges Dumézil, who dedicated significant work to the underlying structure of Indo-European cosmological thought. The Codex Regius itself was written in Iceland in approximately 1270 CE, but the consensus of Old Norse scholarship holds that the poems it preserves reflect oral compositions of the Viking Age, 9th to 11th centuries, with some scholars arguing for earlier strata of material embedded within the poetic forms. The oral transmission of cosmological knowledge in Norse culture was a formal and structured practice, not casual storytelling. The skalds who composed and preserved this material were trained specialists in a tradition that valued precision of memory. The poem, Vafthrûdnismal, extends the cosmological picture. In a wisdom contest between Odin and the giant Vafthrûdnir, the oldest and most knowledgeable being in existence, present at the construction of the world, questions and answers range across the full structure of Norse cosmology. Among the subjects addressed is the behavior of the Sun across cosmic time. The giant describes an interval during which the normal solar order is disrupted, during which light behaves unexpectedly, and during which something described as fire from Muspelheim, the primordial realm of heat and fire, located at the southern extreme of the Norse cosmic map, crosses the sky in a way that is distinct from the normal behavior of fire on Earth. The Muspelheim fire is primordial solar energy, elemental and uncontrolled. Its crossing of the sky is associated with disruption, with the failure of normal conditions, and with a period of instability before restoration. The scholarly understanding of Muspelheim as a cosmological concept is developed in the work of John Lindow, whose Norse mythology, A Guide to Gods, Heroes, Rituals, and Beliefs, Oxford University Press, 2001, provides the most comprehensive modern synthesis of the tradition. Lindow notes that Muspelheim is consistently associated with fire that precedes and follows the current age of the world. It is both the source of primordial fire and the agent of fire at the world's ending. The ambiguity is significant. Muspelheim fire is not ordinary fire. It is the kind of fire that exists before and outside the normal cosmic order. The Norse cosmological imagination, shaped by a northern latitude sky-watching tradition, may have been encoding the most extreme solar events, the Carrington-class eruptions, the events that produce aurora at tropical latitudes, that disrupt compass needles, that cause fire in electrical equipment, as expressions of Muspelheim fire entering the ordered world. The records from 1859, from 1921, from 1989 describe what that fire actually does when it arrives. The Norse records describe what it looks like from the cosmological outside. The scale is different. The phenomenon, arguably, is the same. Völuspá, the prophecy of the Völva, arguably the most important poem in the Norse corpus, contains the most famous description of solar disruption in the tradition. The poem is structured as a prophetic recitation by a Völva, a seeress summoned by Odin, who speaks from the beginning of time through the present and into the future. Among the signs of the approaching change that she describes are a darkening of the sun, a failure of the normal solar cycle, and the appearance of fire from the south crossing the sky. Modern scholars, including Caroline Larrington and Andy Orchard, who have produced the most widely used translations of the poetic Edda, note that the cosmological imagery of Völuspá reflects a sophisticated understanding of cyclical time. The Norse did not understand their cosmological future as a singular apocalypse, but as a phase transition, a disruption of the current order followed by a restoration of a new one. Solar disruption events, in this framework, are not terminal, they are intervals. That framing matters for tonight's report, because the storm now in progress is an interval. It has a beginning, the eruption of active region 4455 on June 3. It has a development, the Cannibal CME formation in transit, the geomagnetic storm now active at Earth's boundary. And it will have an end. Region 4455 will rotate beyond the limb, the magnetosphere will recover, the KP index will return to background levels. The Norse cosmological tradition describes exactly this kind of interval: solar disruption, a period of instability, and return to the ordered state. The tradition is not describing something unprecedented. It is describing something the sky-watching Norse had seen before, encoded in a mythological framework proportioned to the importance of what they were recording. The Vedic tradition presents the same observable phenomenon in a substantially different cultural and astronomical encoding. The Jyotisha, the branch of the Vedas concerned with astronomy and timekeeping, constitutes the oldest continuous tradition of systematic sky observation that has been carried forward to the present day. The Vedic astronomical tradition predates the Babylonian record in some of its formulations and reaches back to a period of active sky observation that scholars place in the 2nd and possibly 3rd millennium BCE. The tradition has been transmitted continuously through oral and eventually written transmission, cross-checked and updated by successive generations of astronomers, and it preserves within its mathematical frameworks and mythological elaborations a record of what the sky actually did across a very long period of human attention. The concept of Ketu in the classical Indian astronomical tradition deserves careful examination because it is frequently misunderstood as purely astrological, as belonging to a system of belief rather than a system of observation. The reality is that Ketu, as defined in the Surya Siddhanta and the Brihat Parashara Hora Shastra, is first and foremost an astronomical designation. It refers to the descending lunar node, the point in the sky where the moon's orbital path crosses the ecliptic from north to south. The lunar nodes precess around the ecliptic in a cycle of approximately 18.5 years, and their positions determine the conditions under which solar and lunar eclipses are possible. The Vedic astronomers tracked this cycle with extraordinary precision. The prediction of eclipse timing in the Vedic tradition is accurate to within minutes, demonstrating that the underlying astronomical mechanics were correctly understood long before the physical explanation of those mechanics was available. What makes Ketu relevant to solar storm research is the expansion of its meaning in the mythopoetic layer of the tradition by the stories and images that encode the astronomical reality in a form transmitted through oral culture. In the myth of Svabhanu, the demon who disguises himself among the gods during the churning of the cosmic ocean and drinks the Amrita, the immortality-granting nectar, Vishnu cuts the demon in half with his discus, before the nectar can pass below the demon's throat. The upper half becomes Rahu, the ascending node. The lower half becomes Ketu, the descending node. The significance of the myth is the relationship it establishes between the severing event and its astronomical meaning. The nodes are the points where paths cross, where what was ascending becomes descending, where the expected trajectory is interrupted. The cutting of Svabhanu is the mythological encoding of the moment when the lunar and solar paths cross. That crossing is the precondition for eclipses, for the temporary disruption of solar light delivery to Earth. The connection to geomagnetic storms runs through the broader concept of Ketu as an agent of disruption to solar energy in transit. In the astrological literature that developed from the Vedic astronomical base, including the Brihat Parashara Hora Shastra, attributed to the sage Parashara and dated by modern scholars to a compilation period of approximately 600 to 1000 CE, the influence of Ketu, when combined with solar configurations, is described as producing disruptions to communication, interference with the normal function of light and heat, and disturbances to established systems that depend on solar energy for their regular functioning. The language is astrological in its application, but observational in its underlying structure. The compilers of the Parashara texts were synthesizing centuries of recorded observation about correlations between celestial configurations and earthly events. When they noted that Ketu solar combinations produced communication disruptions, they were recording a pattern they had seen enough times to codify. Kilke's Comprehensive Study Mathematics and Astronomy in India, Cambridge University Press, 2009 provides the scholarly foundation for understanding the observational precision underlying the Vedic astronomical tradition. David Pingree's multi-decade compilation of Sanskrit astronomical manuscripts, centered at Brown University and now maintained at the American Philosophical Society Library, established the extent and quality of the primary source material. The Surya Siddhanta, which forms the core mathematical text of the classical Indian astronomical system, has been dated by modern scholars to a root composition of approximately the 4th or 5th century CE, with the tradition it encodes extending considerably earlier. The eclipse prediction accuracy of this system has been verified against modern calculations. The Vedic astronomers knew what they were watching. The mythological encoding of what they watched is worth taking seriously as a record of long-term sky observation, separate from its theological applications. The Cannibal CME is, in Vedic astronomical terms, an event of amplified solar energy arriving at Earth through a mechanism that involves the solar energy interacting with itself in transit. Ketu, the descending node, marks the crossing point, the place where paths intersect. The Cannibal CME formed at a crossing point in transit where the faster ejection's path intersected and merged with the slower one. The language is different. The physical process, solar energy transformed through interaction in the space between the Sun and Earth, arriving at a planetary surface as something more intense than what was launched, has a recognizable echo in the mythological tradition. That number in the NOAA advisory, the G4 threshold that remains possible, is the measure of that amplification. We said we would return to it before the end of the report. The Vedic tradition's description of what disrupted solar energy delivery produces connects directly to the G4 effects listed in the NOAA documentation: communication failures, navigation degradation, power system stress. The tradition named the category. The instruments measure the degree. The third tradition in tonight's ancient record comes from the Maya, specifically from the astronomical tables preserved in the Dresden Codex. The Dresden Codex is one of only 4 surviving pre-Columbian Maya manuscripts. It is housed at the Sächsische Landesbibliothek in Dresden, Germany, and has been dated by scholars to the 11th or 12th century CE. Though it encodes astronomical observations of considerably earlier origin, the underlying astronomical tables have been traced by researchers including Floyd Lounsbury and Anthony Aveni to a composition period possibly as early as the 8th or 9th century CE, and encoding observational data extending still earlier. The Codex was brought to Europe from Mexico in the 16th century, recognized as a scientific document by the German scholar Ernst Förstermann in the 1880s, and has since become one of the most intensively studied astronomical artifacts in the world. The Venus tables occupy pages 24 to 29 of the Dresden Codex. They are the most precisely calibrated astronomical tables in the pre-Columbian record, tracking the synodic cycle of Venus, the period of approximately 584 days between successive heliacal risings across a grand cycle of 104 years, at which point the Venus calendar and the solar calendar return to alignment. The Maya identified this 104-year alignment cycle, called the calendar round completion, as a cosmological event of the first importance. It appears in their iconography, in their monumental architecture, and in their ritual practices. The Dresden Codex Venus tables were used not simply to track Venus, but to manage the calendar of dangerous and safe periods associated with Venus's position relative to the Sun. What makes the Venus tables relevant to solar activity research is the specific structure of the danger periods they define. Each synodic Venus cycle begins with the heliacal rising of Venus as morning star, the moment when Venus first becomes visible in the pre-dawn sky after a period of invisibility during inferior conjunction, when it was between Earth and the Sun. The first days of Venus as morning star are described in the Codex's associated almanacs as dangerous, a period when the solar and Venusian energies combine in a configuration that requires ritual attention and behavioral caution. The almanacs associated with the morning star rising include depictions of the god Kukulkan, the feathered serpent, hurling weapons from a circle representing the sky. The weapons are rays of energy. The target is Earth. The scholarly interpretation of this imagery has been advanced by Anthony Aveni of Colgate University, whose Skywatchers of Ancient Mexico, University of Texas Press, 1980, revised 2001, remains the foundational study of Mesoamerican astronomical traditions. Aveni's analysis of the Dresden Codex Venus tables demonstrates that the Maya were tracking not simply the position of Venus, but the relationship between Venus, the Sun, and the geometry of the inner solar system, the same geometry that modern heliophysics uses to understand the directional probability of solar eruptions. When Venus is in inferior conjunction between Earth and the Sun, the geometry of the solar system places Venus in the line between Earth and the source of solar material. The Maya encoded the increased solar energy exposure of these periods in their ritual calendar. They could not measure the KP index. They could observe the sky with extraordinary precision across generations, note the correlations between specific geometric configurations and observable atmospheric and social disturbances, and encode those correlations in a calendrical system sophisticated enough to remain accurate across centuries. The Dresden Codex has been studied from the solar perspective by researchers including Geraldine Patrick Encina and, more recently, by scholars working at the intersection of Maya studies and archaeoastronomy. The consensus is that the Venus tables reflect a level of sky observation extending over at least several generations of systematic recording before the Codex's composition. The Maya were not mythologizing the sky, they were documenting it. The danger periods encoded in the Venus almanacs correspond to actual geometrical configurations of the inner solar system. The weapons hurled by Kukulkan in the Codex imagery represent something that the Maya had observed arriving from the direction of the Sun at specific geometric intervals. We now have instruments that can tell us what that something is. The fourth tradition is the Egyptian, and it is perhaps the most striking in the specificity with which it describes what solar disruptions actually look like from the ground. The corpus of texts associated with the Urt-Ra, the Eye of Ra, is distributed across three major sources: the pyramid texts, inscribed in the burial chambers of Old Kingdom pharaohs, beginning approximately 2400 to 2300 BCE, the coffin texts, inscribed on Middle Kingdom coffins beginning approximately 2100 to 1800 BCE, and the Book of the Dead, which reached its canonical New Kingdom form approximately 1550 to 1070 BCE. Together, these texts constitute the oldest layered theological and cosmological record in the world, and they preserve within their mythological structure a detailed account of how the ancient Egyptians understood the sun and its relationship to Earth. The Eye of Ra is among the most complex symbolic constructions in ancient Egyptian religion. It functions in the text simultaneously as a goddess, as an extension of Ra's power, as a weapon, and as a returning traveler. The mythology of the eye's departure and return forms a complete narrative cycle preserved in multiple versions. The eye departs from Ra, travels outward into the world, and returns having transformed. In some versions, she returns as a benevolent goddess, pacified through music or trickery. In others, she returns as a destroyer, carrying the fire she encountered during her travels, and must be calmed before she reaches Egypt. In the most dangerous versions, she returns with the capacity to burn what she touches, and the priests of Ra must intervene to moderate the intensity of what she has brought back. The relevant texts for tonight's report are the passages in which the eye's return is described in terms of its effect on the world. The coffin texts, which represent the most complete and varied treatment of the eye mythology available to modern scholars, include passages that describe the returning eye as traveling faster than her normal speed, having gathered additional energy during her journey, arriving with a force that exceeds what was present at her departure. The priest astronomers of Heliopolis, who composed and maintained this tradition, were the most sophisticated astronomical observers in the ancient Mediterranean world. They tracked the sun's daily and annual cycles with precision sufficient to align major temples to specific solar events. They maintained calendrical systems capable of predicting the annual Nile flood to within days based on stellar positions. They were not making things up about the sun. They were recording what they had observed. The specific imagery of the returning eye carrying amplified fire, more energy upon arrival than at departure, is a precise mythological encoding of the Cannibal CME process. Understood observationally, the ancient Egyptians could observe that sometimes the sky after a solar eruption was more brilliant, more disruptive, more auroral than the initial event would suggest. They could observe that things arrived from the sun in sequences, that a first disruption was sometimes followed by a more intense second one. They had no instrument to measure the KP index or track a CME in transit, but they had centuries of careful observation of what the sky did, and they encoded the most significant patterns in their most durable documents, the inscriptions in stone that have survived 4,000 years. Eric Hornung's Conceptions of God in Ancient Egypt, Cornell University Press, 1982, English translation, provides the theological framework. Richard Wilkinson's The Complete Gods and Goddesses of Ancient Egypt, Thames and Hudson, 2003, catalogues the Eye of Ra's appearances across the major textual corpora. For the astronomical dimension specifically, the work of Robert Bauval and Adrian Gilbert on stellar and solar alignment in Egyptian architecture has established that Egyptian religious texts were not divorced from observational astronomy. The priest astronomers of Heliopolis were trained observers who operated from a tradition of systematic skywatching that extended from the pre-dynastic period before writing through the entire span of pharaonic civilization. The Eye of Ra texts preserve the output of that tradition applied to the most extreme solar phenomena they had encountered. The answer to the question we posed at the opening of this section is this: 4 separate human traditions, separated by geography, by language, by theology, and by centuries, described solar disruption events because solar disruption events happened, repeatedly, across the full span of human skywatching. The Carrington Event of 1859 was not the first time the Sun produced a major geomagnetic storm. It was simply the first time such an event occurred after a functional global magnetometer network had been established. Before that network, the record was kept by observatory monks in Iceland, by Vedic astronomical compilers in India, by Maya Codex painters in the Yucatan, by Egyptian priest astronomers at Heliopolis. They all saw the same sun. They all recorded what it did. The records are legible, in different languages, across a span of 4,000 years. The data is in the record. The interpretation belongs to you. The Norse tradition warrants deeper examination before we move to the next ancient layer, because the connection between the Eddic descriptions and what modern heliophysics documents is not superficial. The Norse cosmological framework operates on multiple scales simultaneously: the immediate, observable sky, the cyclical time of seasons and years, and the deep time of cosmic ages. The solar mythology spans all three scales, and it is at the intersection of the immediate and the cyclical that the connection to geomagnetic storms becomes most visible. Consider the specific behavior attributed to the sun-wolf shoal in the Eddic tradition. In Grímnismál and its prose summaries in Snorri's prose Edda, two wolves pursue the sun and moon across the sky, Skuld chasing the sun, Hati chasing the moon. The wolves do not catch their prey in ordinary time, but in the mythological future, they do. The sun is swallowed, the world goes dark, and the Great Disruption follows. Modern scholars, including John McKinnell, have argued that the wolf pursuit mythology encodes an observation about solar eclipses. The periodic apparent reduction of solar light that a solar eclipse produces would, to a sky-watching culture without an optical explanation, look very much like something swallowing the sun. This reading is convincing as far as it goes, but the mythology also preserves something more specific than eclipse observation. The phrase in Grímnismál describing the sun's shield, Svalin, the cooler, uses the word that, in Old Norse, refers to the moderating of heat, the interposing of something between fire and its target. The same word appears in other Old Norse contexts to describe the specific act of placing a barrier between an intense heat source and a surface that would otherwise burn. The Norse had practical experience of this kind of moderation through their metalworking tradition. The smithy required careful management of heat, the interposition of tools and barriers between the fire and the material being worked. The vocabulary of the sun's shield is the vocabulary of heat management. It is the vocabulary of people who understood, in practical terms, what happens when a moderating barrier between a fire source and its target is removed or fails. What happens to Earth's magnetic shield during a major geomagnetic storm is precisely this. The magnetosphere, which normally deflects the bulk of the solar wind around the planet, is compressed and partially penetrated. The pressure of the arriving CME pushes the magnetopause, the outer boundary of Earth's magnetic field, inward on the day side, closer to the planet than its undisturbed position. The night side magnetosphere stretches into a long tail and periodically collapses in a process called magnetic reconnection that injects energetic particles into the inner magnetosphere. The shield is not destroyed, but it is deformed, compressed, and in some regions effectively penetrated. The energy that Svalin normally diverts flows through. The mountains and the sea feel it, not as fire, but as geomagnetically induced currents in the ground, as radiation exposure for high-altitude travelers, as visible light at latitudes that normally see none. The vocabulary is different. The physical process is recognizable. The Vedic expansion requires attention to the concept of Rahu as well as Ketu, because the two nodes operate as a pair, and their interaction with the sun defines the full Vedic framework for solar disruption. Rahu, the ascending node, is the point where the moon's orbit crosses the ecliptic, moving from south to north. In the mythology, Rahu is the upper half of Svarbhanu, the head, which retained the nectar in the throat briefly before the severing. Rahu's influence in the astrological tradition is described as obscuring, swallowing, consuming. When Rahu is conjunct the sun in the classical texts, the sun's light is described as being consumed or hidden, an encoding of solar eclipses, which are only possible when the sun and moon are near the nodes. But the broader mythological meaning of Rahu's relationship to the sun extends beyond the eclipse mechanism. Rahu consuming the sun is the consuming of solar energy at the source, a reduction in solar delivery. Ketu's influence is the opposite in structure, but complementary in function. Where Rahu reduces, Ketu disrupts. Where Rahu swallows, Ketu disturbs. The Ketu tradition in the astrological literature is consistently associated with the unpredictable, the sudden, the arrival of something unexpected from a familiar direction. A Cannibal CME is the sun, a familiar direction, producing something unexpected, two ejections that merged mid-transit and arrived as one amplified object not predicted by either individual CME's trajectory. The Vedic astronomical framework, operating without modern instruments, but with centuries of careful correlation between celestial configuration and observable terrestrial phenomena, encoded this category of solar event, the amplified, unexpected solar delivery, in the mythological language of Ketu's disruption. The language is not the mechanism, but the category of event it describes, solar energy arriving at Earth in a form more intense than the ordinary delivery, producing disruptions to communication and established systems, matches the NOAA category currently active. The transmission history of the Brihat Parashara Hora Shastra, the primary text for the classical Indian astrological tradition, is relevant here because it demonstrates the care with which this material was preserved. The text is attributed to the sage Parashara and is understood in the tradition to preserve teachings of much earlier origin, transmitted orally through a formal disciplic succession before being committed to Sanskrit text. Modern scholars date the compilation of the current version to approximately 600 to 1000 CE, with the astronomical content encoding observational data of considerably earlier provenance. The eclipse calculation methods in the text, which are precise enough to be verified against modern computations, could only have been developed through long periods of systematic observation. A tradition that was precise enough to calculate eclipse timing to within minutes was also precise enough to notice that certain solar configurations correlated with atmospheric and electrical disturbances at ground level. The Ketu solar correlation documented in the tradition reflects that noticing. The Mayan tradition invites additional examination because the Dresden Codex is a living document in the sense that it has been studied for over 150 years by an increasingly sophisticated body of scholars, and the understanding of what it records has deepened substantially in that time. Ernst Furstermann's initial analysis in the 1880s identified the Venus tables as astronomical. J. Eric Thompson's mid-20th century work refined the correlation between the Maya long count calendar and European dates, making the Codex interpretable in absolute time. Floyd Lounsbury's landmark work in the 1970s and 1980s established the specific astronomical mechanics underlying the Venus table's construction. More recent scholarship by Susan Milbrath, by David Friedel, and by scholars working at the intersection of Maya epigraphy and archaeoastronomy has continued to refine the picture. What the accumulated scholarship establishes is that the Maya astronomical tradition was empirical before it was religious. The observational data came first. The ritual and mythological encoding of that data came second, as a means of transmitting and applying the observational knowledge in a culture without writing for most of its history. The Venus tables are not a religious document that happens to mention astronomy. They are an astronomical document that has been given religious encoding to ensure its preservation and application across generations. The danger periods they define are danger periods because the Maya had observed, across sufficient iterations, that those periods correlated with elevated risk. The observation preceded the definition. What the risk consisted of, what exactly arrived from the direction of the Sun during Venus morning star periods, is what modern heliophysics is equipped to specify. The Maya named the interval. We can now name the content of the interval. The Egyptian tradition is similarly deep in its evidential basis. The pyramid texts, the oldest layer of the Eye of Ra material, were inscribed in burial chambers at Saqqara, beginning with the reign of Unas, approximately 2375 BCE. They were not composed for that occasion. The linguistic analysis of the pyramid texts indicates that their language is archaic relative to the Egyptian of the Old Kingdom period. They preserve grammatical and lexical features that were already old when they were first inscribed. The tradition they encode extends into the pre-dynastic period, before hieroglyphic writing. The priest astronomers of Heliopolis who maintained and transmitted this tradition were the institutional memory of Egyptian skywatching from before the state itself existed. The Eye of Ra texts preserve within their mythological structure a specific claim about solar eruption events, that what returns from the solar journey is changed from what departed. The eye goes out from Ra, and what returns is described in the Coffin text and Book of the Dead versions as having more fire than when she left, having gathered energy in transit, arriving with an intensity that requires management. This is not a prediction of solar physics. It is an observation of what happens when a major solar event arrives at Earth. The aurora is more brilliant than any simple flare would produce. The compass needles behave strangely. Things that carry electricity behave unexpectedly. The eye's return is the arrival of the solar storm. The priests knew something was coming back. They could see it in the sky. They recorded the category of the event in their most durable medium, and that record has survived 4,500 years. The comparison of all four traditions produces a convergence that is worth stating directly. The Norse, Vedic, Maya, and Egyptian traditions are separated by geography, by language, by theology, by calendar system, and by the specific cultural contexts from which they emerged. They have no documented historical contact with each other relevant to the sky-watching traditions in question. Yet all four describe, in their respective mythological encodings, the same category of physical event. Solar energy that departs from the Sun, is transformed or amplified in transit, and arrives at Earth with greater intensity than the normal delivery, producing disruptions to established systems, visible displays in the sky at unusual latitudes, and a period of instability before the restoration of ordinary conditions. The convergence is the product not of communication between traditions, but of observation of the same sky. The Sun was doing this before human records existed. The traditions that survived long enough and were careful enough in their sky watching are the ones that caught it. Tonight, the instruments are catching it in real time. The 3-hour KP index updates through the night. The DSCOVR spacecraft monitors the approaching solar wind. The magnetometer networks across North America, Europe, and the Southern Hemisphere log the magnetic field changes at the surface of the planet. The aurora is visible or not visible, depending on where you are and what the storm is doing. The four traditions we have examined tonight would not be surprised by any of this. The sky, in their understanding, has always been capable of it. We have simply added the instruments to confirm what the observation already knew. The solar cycle context for tonight's event rounds out the picture. We are currently in solar cycle 25, which began in December 2019 and has been more active than many forecasters predicted in its early stages. The cycle's peak, solar maximum, was expected around 2025, and the Sun has been producing elevated activity consistent with that timing. Active region 4455 is one of many complex sunspot groups that have appeared during the current cycle's most active phase. The triple flare sequence of June 3 and the Cannibal CME now arriving represent the kind of output that solar maximum conditions make more probable, though not inevitable. The Sun does not schedule its major eruptions. It produces them when the magnetic conditions in a specific active region reach the threshold for instability. Region 4455's anti-hail configuration, its continuous flux emergence, and its sustained magnetic complexity created those conditions. The timing, during a period of elevated solar cycle activity, increased the probability that a region with those properties would appear, but the specific sequence of events on June 3 was not a solar maximum prediction, it was a solar maximum delivery. As this report is filed, the Cannibal CME is arriving at Earth's magnetic boundary. The geomagnetic storm it is driving is live. The KP index is updating in 3-hour increments through the night. The G3 strong level that NOAA has confirmed represents the floor of what this event will produce. The G4 severe level that remains in the active advisory represents a ceiling the storm has not yet reached and may reach, depending on the magnetic orientation of the solar wind at arrival. Here is what we are watching in the hours ahead. The DSCOVR spacecraft at the L1 Lagrange point will provide the critical BZ orientation reading when the leading edge of the merged CME reaches that position. A sustained southward BZ, the key variable, is the condition that would drive storm intensity from confirmed G3 toward the G4 threshold. NOAA SWPC publishes real-time BZ data at swpc.noaa.gov, updated continuously. The 3-hour KP readings, published on the same platform, are the clearest summary metric for storm development. A KP of 7 is G3 confirmed. A KP of 8 is G4 severe. The difference between those two numbers, in terms of aurora visibility, is approximately 10 to 15 degrees of latitude. The difference between aurora reaching the Pacific Northwest and aurora reaching Los Angeles. Active region 4455 remains the second monitoring priority. The region has not yet rotated beyond the geoeffective window, the zone on the solar disk from which Earth-directed CMEs can be produced. NOAA's forecast through June 5 assessed M-class flaring as likely from region 4455 and from the additional active regions 4458, 4461, and 4,462. A new significant flare from any of these regions before 4,455 rotates to the western limb, expected within approximately the next 5 to 7 days, could extend the active period and produce a third wave of CME material arriving at Earth, while the magnetosphere is still recovering from the Cannibal CME's passage. Space weather physicists describe this condition as a complex event, and complex events are the ones that produce the most variable outcomes, because the magnetosphere's response to a second or third arrival depends heavily on the state of its recovery from the first. There is also the secondary arrival flagged in the current data, a component of the CME from an M3 flare on June 2, the day before the main triple flare sequence, may arrive at Earth on June 6, producing an additional period of enhanced geomagnetic activity on top of any lingering effects from the Cannibal CME. The monitoring window does not close when the Cannibal CME passes. It closes when the solar wind returns to undisturbed background levels, and region 4,455 has rotated beyond the limb. The 4 traditions we examine tonight describe solar disruption as an interval with a defined structure: departure of energy from the Sun, transformation in transit, arrival at Earth in a changed form, disruption of normal conditions, and eventual restoration. The Norse interval of Muspelheim fire crossing the sky ends when the fire passes and the sky returns to its ordered state. The Vedic Ketu influence, measured by the nodal cycle, has a duration and an endpoint. The Maya danger periods associated with Venus morning star risings are bounded by specific day counts that define when the dangerous period is over and the regular calendar resumes. The Egyptian Eye of Ra mythology describes not just the departure and the destructive return, but the calming, the ritual intervention that moderates the eye's intensity and returns the solar energy to its normal delivery pattern. All 4 traditions encode the same structural observation: solar disruption events are intervals. They have beginnings and ends. The sky, eventually, returns to its expected behavior. Tonight's interval began June 3. It is active now. It will end when region 4,455 rotates west of the limb and the magnetosphere fully recovers. The instruments will track every hour of that interval. We will remain in observation. If what this channel files each night is the kind of reporting that matters to you, the live data from the agencies, the documented historical precedent, the older human record set alongside the current numbers, in a format that does not sensationalize and does not fabricate, then the most direct thing you can do to support this work is to subscribe. We file every night. The data does not pause between events, and neither do we. There are viewers who have been here since the first broadcast and have watched this channel build the archive that calls 0 of tonight's ResearchGate searched. That archive is what makes the pattern visible. A single report is a data point. A series of reports across months and years is a pattern. You are watching the pattern being built, one night at a time. If tonight's report reached you through a share or a recommendation, that action matters more than you may realize. The channel grows through exactly that mechanism. One viewer telling another that something is being documented here that is not being documented anywhere else in quite this way. The combination of official agency data, multi-century historical record, and the oldest human textual traditions, presented in a single uninterrupted documentary format, is what we do here every night, without exception. Leave a comment, share the report, and tell us where you are watching from tonight. If the aurora is visible from your location, we want to know. Drop the city and the sky description. The comment section builds its own record. We continue to monitor. We will report again at last light. The monitoring window for this event will remain open through at least June 6th, and possibly through June 7, if region 4,455 continues producing significant flares before rotating beyond the western limb. What this means in practical terms is that the 3-hour KP readings, the real-time solar wind data from DSCOVR, and the magnetometer network outputs will continue to update throughout tonight and tomorrow, providing a continuously refined picture of how the storm is developing and whether it holds at G3 or escalates toward G4. The practical steps for viewers in high-risk geographic areas are documented and publicly available. For Aurora watchers, the NOAA SWPC 3-day forecast at swpc.noaa.gov is the authoritative source for storm level predictions and aurora latitude estimations. SpaceWeatherLive.com provides real-time KP index tracking with a historical graph showing how the index has moved through the past 24 hours. Dark skies and a northern horizon with low obstruction are the viewing requirements. Under G3 conditions, viewers at latitudes above 50 degrees north should have clear visibility with favorable sky conditions. Under G4 conditions, the latitude requirement drops to approximately 45 degrees north, covering large portions of the continental United States, including the northern Midwest, New England, the Pacific Northwest, and comparable latitudes in Europe and Asia. For viewers in regions with aging power infrastructure at high geomagnetic latitudes, the North American Electric Reliability Corporation, NERC, maintains a public page at nerc.com that includes information about geomagnetic disturbance planning standards and the protective measures that have been implemented since 1989. The individual utilities in the highest risk regions, Hydro-Québec, the transmission operators in Scandinavia, the utilities in the northeastern United States, have GIC monitoring active on their networks and are watching the same KP index data that we are watching. They have procedures for protective action when the thresholds are crossed. Those procedures are better than they were in 1989. How much better is the question that tonight and tomorrow will help answer. The four traditions we examined in the ancient records section tonight, the Norse Eddas, the Vedic Ketu tradition, the Maya Dresden Codex, and the Egyptian Eye of Ra corpus, all describe the same fundamental category of interval. Solar energy departs from the Sun, is transformed in some way during transit, arrives at Earth with greater intensity than the ordinary delivery, produces disruptions that are visible in the sky and felt in systems on the ground, and eventually subsides. The traditions differ in their mythological frameworks, in the specific imagery they use, in the ritual responses they prescribe, but they agree on the structure of the event. They agree that the arrival of amplified solar energy at Earth is real, recurrent, and consequential. They agree that it ends. They agree that the normal order, eventually, is restored. File tonight adds to that agreement is measurement. We know the KP index is tracking G3 and G4. We know the CME arrived as a cannibal structure, merged from two individual ejections. We know that DSCOVR will confirm the BZ orientation in real time, and that the confirmation will update the forecast for the remainder of the storm's active phase. We know that region 4455 is still geo-effective and still producing. And we know, from four traditions that span more than 4,000 years of skywatching, that this category of event is old enough to have been witnessed, recorded, and encoded in the most durable documents that human cultures produce. The ancient record is not a curiosity. It is the long baseline confirmation that what we are watching tonight has been watched before by people who had no less interest in understanding it than we do, and who had more time to observe the pattern. The instruments are running. We remain in observation. We will file again when the data warrants. If you have stayed with this report through to the end, through the live NOAA data, through Carrington and Quebec and the 2024 storm, through the Norse Eddas and the Vedic nodes, and the Maya Codex and the Egyptian Eye, then you know what this channel does and why it does it this way. The depth is the point. The pattern is only visible if you look at the full span of the record, from tonight's KP, updates back to the inscriptions in the burial chambers of Saqqara. Subscribe to stay in the record. Leave a comment to add your location to the map. Share this report with one person who should be watching the sky tonight. These are the things that keep the channel operational and the nightly filing continuous. We continue to monitor. We will report again at last light. The solar wind data streaming from DSCOVR tonight is the same data that powered the protective actions in 1989, the same data reconstructed in retrospect for 1859, and the same data that the Norse, Vedic, Maya, and Egyptian skywatchers observed with their eyes and encoded in their records. Different instruments, different languages, same sun, same earth, same interval. We remain at the instruments. The record stays open. One final monitoring note before this file closes. The particle radiation environment during a major geomagnetic storm is not limited to the magnetospheric effects that drive the KP index. Energetic protons accelerated by the initial flare events and by the interplanetary shock associated with the CME arrival can penetrate to polar latitudes and produce what NOAA classifies as a solar radiation storm, rated on the scale from S1 to S5. The current event was not produced a significant scale event, with proton flux remaining at background levels through the storm's initial phase. This is a notable absence from the data because it suggests the CME's interaction with the heliospheric current sheet during its Cannibal merger may have reduced the particle acceleration that typically accompanies the strongest interplanetary shocks. It is one of the ways in which tonight's storm profile differs from a simple single CME event of comparable KP intensity. We log the absence as well as the presence. The record is more complete for noting what is not there.